Welcome back. So now we would like to understand the current flow in a PN junction more quantitatively. To do that, we need to understand how the minority carrier injection takes place. So what is minority carrier injection? So we have seen that we have a p-type semiconductor and an n-type semiconductor. So the majority carriers are, here in this case it is holes, here electrons. Okay. It turns out that the, the current flow in a PN junction is not dictated by the majority carriers, but it is actually dictated by the minority carriers. Okay. So what are the minority carriers now? Minority carriers in case of p-type semiconductor are electrons, and on the n-type it is holes. Okay. How these carriers flow is what is going to influence. Okay. So to understand that, we will actually draw a diagram multiple times today. So I'll just take a moment to just quickly run through that. So what we would like to plot is the minority carrier concentration as a function of position. So what I'll do is I'll take, let me say, x-axis. Okay. And on the y-axis, I would like to plot the minority carrier concentration. So I'll just first denote my minus xp, which is the edge of the depletion region on the p side, and xn, which is a depletion edge of the depletion region on the n side. So once I have this, what is the concentration of minority carriers in the n-type semiconductor? So the concentration of minority carriers I'll represent by, let me take this. So this is my, I'll say P, holes of the minority carriers, so P, but in the n-type semiconductor, and equilibrium minority carrier density is what I want to first find out. Okay. What is it going to be? Well, this is going to be, the same thing that we've been doing. So Ni square divided by in the n-type region, the majority carriers are the electrons. So electron concentration is going to be Nd, and the whole concentration at equilibrium is going to be Ni square by Nd. So I'll represent that in the axis here. And same thing I want to do on the p side. Okay. So how would you do that? So I can say there will be in this case, electrons are the minority carriers. So N, and just to denote that it's on the p side, I will put it as Np naught. I hope the notation is clear. If not, just take a moment, rewind the video, and then take a look at it. Okay. So essentially, we want to know the minority carrier density in both regions. Okay. Here, this is equal to Ni square divided by Na. All right. So this is how the equilibrium minority carrier concentrations are without any applied voltage. Right? Now, what happens when we apply a voltage? Okay, that's where a lot of interesting things happen, right? So, when we apply voltage, we said that we are actually injecting holes into the N side. Similarly, we are injecting electrons into the P side, right? So essentially, applied voltage is injecting, VA causes injection of minority carriers, right? Because we see that this is an n-type semiconductor and we're injecting holes into it. Similarly, into the p-type semiconductor we're injecting electrons. Okay. So the question we want to ask is, what is the concentration of holes at the edge of the depletion region? So I'll say concentration of holes in the n-type semiconductor at Xn is equal to how much? Okay. That is very important for us, because once we know that, we can find out what happens further into the n-type semiconductor. Similarly, I want to find out what is the concentration of, in this case it's a p-type semiconductor, so we need to know the concentration of electrons in the p-type semiconductor at minus xp. If I know this, then I can determine the rest of the concentrations, because I have the minority carrier diffusion equation with me, right? So how do we determine this? Remember, this quantity P of n is a non-equilibrium situation. It's going to be higher than the Pn naught. Pn naught was equilibrium density, and we saw that Pn naught was relatively low, right? Because the doping was 10 power 14, 15, 16, whatever, and correspondingly the Pn naught will be lower, right? But now we are taking the majority carriers on the P side, which is a lot of them. It can be 10 power 16, and then we are injecting into the other side of the barrier. And we saw the barrier width was about 1 micron or so, right? That was a typical number I said. So we are easily injecting holes into the N side. So we are like putting too many minority carriers, right? So what happens? Okay, how do we determine this? Well, to understand the minority carrier dynamics, or whenever you have non-equilibrium situations, we introduce the concept of quasi-Fermi levels. So we'll make use of that. So I would like you to review, or try to recollect the carrier densities in terms of the quasi-Fermi levels. So what are they? So for electrons, we said electron concentration. Remember, I'm not writing the N naught. I'm not writing the equilibrium electron concentration, but I want to write the non-equilibrium electron concentration, and that is given by the quasi-Fermi level, right? So this is going to be Ni exponential. EF is going to be higher than EI for a N-type semiconductor. So EFN minus EI by KT. This is the definition of the quasi-Fermi level for a N-type semiconductor. For an electron, right? And what about the P? For the holes, it is going to be Ni exponential. If it's a P-type semiconductor, it's going to be lower than EI. So that's why it's going to be EI minus EFP by KT. Okay. Remember, I always, I guess for me, the way I remember it is, I'm using this as a reference level, Ni. My majority carriers are going to be higher than that. I just think about that and then I put my appropriate sign. Otherwise, there's a chance of getting confused with the sign in the exponential. Okay. So please form your whatever works for you. You just figure it out. All right. Okay. So you have these non-equilibrium. I won't write it. Non-equilibrium carrier densities. Right. So what? Well, you can take an NP product. Right? I said non-equilibrium means it's not equal to 0. Ni square. I said it's not equal to Ni square, right, for NP product. But now what exactly is it? So it turns out that if you take NP product, N into P is going to be Ni square exponential EF N minus EFP by KT. Right? So EA is going to get cancelled out in the exponentials and you get this. And what is this? This is simply equal to Ni square equal to exponential Q times V applied divided by KT. Okay. How does this help us? Well, it helps us because remember, why did I write applied voltage? You have to go back to the band diagrams we discussed in just the previous video, right? We said that the difference in the Fermi levels in the N and the P is basically the applied voltage. Okay. So now, how does this help us? Well, this is going to be applicable, right? This is valid. This is actually a very, very important relation. We call it actually the law of the junction. Okay, we just give it a name, but this is a very, very important relation in a PN junctions. Okay. So what happens is, what this is telling us is, this is valid all across the PN junction. All right. So now we'll try to apply it. Right? So let's try to apply first at this point XP minus XP. So what is N? N is going to be electrons in the P-type semiconductor at minus XP times the holes in the P-type semiconductor at minus XP is equal to Ni square exponential QV applied divided by KT. Okay. What is the number of holes in the P-type semiconductor? So this is going to be equal to Na. Okay. So what I'll do is I'll simply make this Na go here. Okay. I'll do divide by Na. And if I do this, this guy is going to be NP naught. Okay, right? It's the number of electrons, equilibrium density of electrons, right? So, with all the rearrangements, just take a moment, analyze it yourself. This is fairly simple. So basically what we are saying is NP at minus XP. That means at the edge of the P region is going to be the equilibrium electron density multiplied by exponential QVA by KT. That's it. So we already know here, for example, this is the equilibrium electron density. I am taking that and multiplying it by exponential the applied voltage, QVA by KT. Then I get my electron density at the edge of the depletion region. Similarly, I can do the same analysis at Xn. We are writing simply NP product. Okay, it's nothing complicated. NP product, right? So here it's an N-type semiconductor. So I'll write electrons in the N-type semiconductor at my point Xn. Xn is the edge of the depletion region. At that point I want to know, multiplied by the holes in the N-type semiconductor at Xn should be equal to Ni square exponential QVA by KT. Okay. So this is my law of the junction, right? Basically, NP product should be equal to Ni square exponential QVA by KT. When VA is 0, it becomes equilibrium situation. NP square equal to Ni square. Okay. So now what is this? Well, this guy is simply ND, and I'll take it to the other side. Okay. So I'll move it here to the other side and divided by ND. And if I do this, this entire thing is going to be Pn naught, the equilibrium hole density in the N-type semiconductor. Right. So my Pn at Xn is going to be the equilibrium density Pn naught exponential QVA by KT. That's it. So just by applying voltage, I am exponentially increasing the minority carriers at the edge of the depletion region. Okay. So this is what is happening. So now, how does this help us? Well, I mean, we are actually, let's clean it up. So this is, I hope this is, clear. In a video, we go a little fast because there is no response, there is no feedback from the students. So it might be a little fast. So if you are not sure, please take a few minutes and then pause it and then go back and review it. All right. So this is my minority carrier densities at the edges of the depletion region. So I'll put it in a cleaner way. So the same thing, just in a more presentable way. So the edge is, your equilibrium density of holes was lower, much lower. And now you have the excess minority carriers, which is, on the scale here. Similarly, the electrons were low, but because, this electron injection has happened across the depletion region, okay, there is an excess minority carrier density in the N-type region. Okay. Well, we made a very implicit assumption without actually specifying it. Okay. So the assumption we made was there is no generation or recombination in depletion region. Okay. This is actually not a very strong assumption. I mean, it's not a well qualified assumption, I would say. The reason is, whenever you take semiconductor out of equilibrium, it will try to come back to equilibrium. Okay. So we saw that if you introduce excess electron hole pairs, they will recombine and come back to equilibrium. Similarly, if you remove electron hole pairs, that is what we did in the depletion region, electron hole pairs will be generated and then it will try to come back to equilibrium. So there is going to be some generation of electron hole pairs. That is going to influence your current slightly. Okay? But for now we are neglecting it. The reason is uh, it makes our mathematics simpler for now. And in the end, we'll show you the effect of violating this assumption. It's not going to be that significant. So we say, okay, it's fine, even if we neglect it. Okay. So we say, it's a kind of a roundabout way of proving something, right? If you want to prove x equal to y, we can start out by actually saying that x is not equal to y. But if you do that, you're still consistent. So, x equal to y is okay. It's not, sorry, x is not equal to y is not consistent. So x has to be equal to y. That's sort of a proof, right? We are doing something similar here. Okay. So essentially, when we are saying that there is no generational recombination, we are saying that Pn and Np does not change across depletion region. All right. Okay, so this is what your excess minority carrier looks like. Now, let's do a quick sanity check. I mean, I mentioned this, but just for completeness, let's say if Va equal to 0, what happens? Your minority carrier density, Pn, is going to equal to Pn naught. Similarly, Np is equal to Np naught. So this is equilibrium. Only when applied voltage is not equal to 0, then you have non-equilibrium situations. Okay. Now, the next question is, how does the minority carrier density change with position? So all we have done so far is, we know the minority carrier density at the edges of the depletion region. How does it change with position? Okay. Change with x. Think about it. Or, you might recall in the third week, I think we have done, we have discussed the minority carrier diffusion equation, MCDE, right? So we have taken a situation wherein you have, let's say, a semiconductor, and somehow we are introducing some minority carriers here. So I said this was, let's say, if it's an n-type semiconductor, you have introduced, let's say, P and at 0 point, and then assume that you have reached steady state. You applied a voltage or current, applied a voltage and waited. Okay. So we are introducing a steady number of Pn naught, Pn at 0. What happens to the density as you move into the semiconductor? So we have taken the case of, we have to steady state and diffusion terms were there, right? I don't remember which case it was, but one of the cases was this. Okay. So we saw that when you have a situation like this, there's going to be an exponential decay. Right? That's exactly what, we will not solve it now. If you are not convinced, go back and look at that particular lecture and it will become clearer. So what our analysis told us is, this is simply going to be Pn naught times exponential Q times Va by Kt at the edge. And then if you're going into the semiconductor, here this is going to be simply exponential minus x by L. Is it going to be P or Ln? Okay. It's going to be minority carrier diffusion length. So this is going to be Lp. Okay. Similarly, on this side, this is going to be exponential x by Lp. Ln, sorry. Here minority carriers are electrons, so it's going to be xl. I removed the minus because x is minus on this side, so I just left it for that. So x is going to be minus, so it's going to decay. Okay. And we know, of course, this is basically np naught exponential QVA by KT. Okay. So you have these excess minority carriers, and they're going to decay into the semiconductor. Okay. And how was this obtained? This is actually obtained by solving MCDE. Okay, so I mentioned that you have essentially this point is a source, excess minority carriers at XP. Sorry, this is XN, right? This is XN, and for all x greater than XN, it's going to be yeah. Okay. In fact, if you want to be exact, I should correct myself here. This is not simply x. This is x minus xn, right? Because at x equal to xn, this is going to be the maximum Pn naught into exponential QVA. Okay. Well, that is okay, but you get the picture what it is, right? That's a more exact way of representing. All right. So now what happens to the band diagram? Okay. The band diagram becomes slightly more complicated. But we know what happens whenever you have a decay, exponential decay in the minority carriers, that will show up as a straight line on the band diagram, right? So we have taken the original, forward bias PN junction. So this is basically lower. So this is going to be my Q times VBI minus V applied. So the barrier has reduced. And you have the majority carriers, which are electrons here. And the majority carriers is more or less same, but we have injected a number of minority carriers here. Okay. So basically this is showing you that minority carriers, I'm sorry. So yeah, here you have electrons and you are injecting them into the p side. The moment you come into the p side, it essentially becomes minority carrier, right? So this is my point of excess electrons. And here, this is excess holes, which are minority carriers. And as you go deeper into the n-type semiconductor, these holes will recombine with electrons, and eventually the quasi-Fermi level will go back and merge with the Fermi level. Okay. So similarly, on the p side, we have injected electrons here, which are the minority carriers. As we go deeper into the p-type semiconductor, the holes will recombine with electrons. Sorry, in this case, electrons will recombine with holes, and then they go back to the equilibrium Fermi level. So remember always, this is the majority carrier Fermi level, right? So majority carrier Fermi level does not change much, change significantly. There's going to be some slope, but it's very small. Of course, it also depends on how much excess minority carriers you introduce. If you have introduced a lot of minority carriers, then it will change. Anyway, that was electron hole production. In the case we discussed for the MCDE in the week 6, I think it was lecture 6, I believe, or lecture 5. So there we are producing both electron and holes, but now we are simply injecting only electrons or holes. Okay. So the majority carrier line, the EF for the majority carriers is going to be flat. Okay. So if you look at this band diagram, can you tell me where is the semiconductor in equilibrium, where it is not in equilibrium? Well, it is in non-equilibrium for minus x. Well, actually, this is minus xp, let's say. This is xn. So it is going to be non-equilibrium for a few diffusion lengths, right? This is basically few diffusion lengths, few LPL, write it. Sorry, this is for p type, so ln, few ln. Similarly, this is few LP. So for the entire region here, spanning the depletion region and a few diffusion lengths outside that as well, this is going to be non-equilibrium. Okay, everything else outside is in equilibrium, so that's why we see that the Fermi level is constant. There's only one Fermi level. Whenever you have splitting of Fermi level into two quasi-Fermi levels, that's a sign that we are in non-equilibrium situation. Okay. So we have excess, in this case, excess holes. Here you have excess electrons. Okay. How do we know that it's the minority carrier? Because minority carriers will change. Majority carriers are not changing, right? You don't need to know much. You just, I can give you this, just these lines, which are the band diagrams, and then that will tell you everything you need to know. Okay, so it's that simple. So uh, yeah, this essentially clears up the concepts. Let me take a few minutes to just solve a numerical problem so that we get an order of magnitude, we understand how much it is. Okay? So to do that, here is a simple problem from the textbook, example 8.1. So please go back and refer if you have any concerns or doubts. And then we are essentially talking about forward bias PN junction with a ND given, NA given, and there's an applied forward bias voltage. And we are asked to calculate the minority carrier concentrations at the edge of the space charge region. Okay, minority carrier concentrations. So essentially, let's draw the diagram. I want you to practice it. I want you to be comfortable because every time you draw these diagrams, your concepts are going to become more and more clear. So let me put this up. So let me say there is X, and then there is a depletion edge, and there's another depletion edge. So this is my Xn, this is my Xp. Okay. So I want to show the carrier concentrations here. So what will it be for the N-type semiconductor? This is N-type and this is P-type and this is in between depletion width. So in the N-type semiconductor, we're going to talk of P and naught, equilibrium density of holes, and that is going to be equal to Ni square divided by the donor concentration. In this case, this is 10 power 16. Okay, so I'll say this is approximately 10 power 4. I'll leave it there. Okay. What about the P-type semiconductor? P-type has a slightly lower carrier concentration, sorry, lower doping density. So the minority carrier concentration is going to be slightly higher. So here I want NP naught equal to Ni square divided by 6 into 10 power 15. Okay. So, I mean, it will be some number you could just calculate. I'll take it as 5, so it will be 2. If I'm not wrong, it should be something like 2 into 10 power 4, maybe something like that. Okay. So please make sure that you verify these answers. So you have the initial equilibrium densities. Now, how do you find the total minority carrier concentration for a forward bias? So it is going to be somewhere here. The holes is going to be higher than the equilibrium density, right? And this is going to be equal to P n naught exponential applied voltage is 0.6. Okay. So, I mean, you could write it as Q times applied voltage, VA divided by KT, but I will simplify it. I'll say that, okay, we saw it was 10 power 4 exponential. Q times VA in electron volts is going to be 600 or, 0.6 electron volts. I'll write KT in electron volts, which is 26 or 0.026 electron volts. Okay, so this is going to be 10 power 4 exponential 25, right? You take it as 25. So 4 times 6, 24. So exponential 24. Please try it out, okay? Something like that. So it's going to be a very large number. I think if you compute it, it's going to be something like 10 power 14 or 15, something, some number like this. Okay. So we are injecting a very high amount of minority carriers. It's not a small amount of carriers. Okay. Relative to, of course, the starting doping, minority carrier density was very small, 10 power 4, and we have essentially introduced almost like 10 power, 10 orders of magnitude higher holes into the N-type semiconductor. Similarly, I could do the same thing in the P-type semiconductor. Okay, so the problem requires you to calculate both of these. Okay, the point you need to remember is that excess minority carriers are significant, okay, when compared to equilibrium minority carrier density. can't ignore this. Okay. Of course, we are assuming still that, let's say if you're talking about force injected into the N type, that is less than N naught. The majority carrier density, it's still less than majority carrier, when low level injection is present. If you have even more than that, then we break down some of these assumptions and our analysis will not be accurate. Our analysis is accurate as far as your introduced minority carriers are still less than the majority carriers and significantly greater than the minority carriers. So please, it is not, for many of you, this is probably the first time you're going to see this, and we are actually focusing on, significantly on the qualitative understanding. Okay, we are really developing very, very strong fundamentals. If you are able to follow along with this course, I mean, it gives you a solid foundation to study semiconductor devices at a graduate level or PhD level. Okay? So please make sure that you spend the time. I mean, even if you don't want to do research, even in the GATE exams, I see that sometimes you have all these problems. What is excess minority carrier density and so on. So these days, for the last 4 or 5 years, there have been increasingly larger number of problems from semiconductor devices, and so that this will help you answer all that. Okay? Even if you're not interested in the research aspect, but I would urge you to look at it carefully. All right. Thank you very much. So I'll stop here. It's already close to 1 hour. We'll take up in the next lecture, where we will derive the expressions for current in a semiconductor. Okay. All right. Thank you so much. We'll meet later.